lütfen birbirinizin yeni imza atma olmasın. Okay, last time I guess we stopped at this point. We were talking about the directories, and we said that this hierarchical directory system, people started using this long time ago. We are still using it. It has some shortcomings, but it is okay. We can find some solutions for those. For example, what was the main problem that I mentioned last time? I said that a file doesn't have to belong to, I like my file to belong to more than one directory, and in this case, since this is a tree structure, in tree structure, it is not possible. But by means of sharing files, I can draw this kind of links. So this file B is shared by this directory A and this B. I can have this kind of structure. Instead of having a tree, now this is like a directed graph, right? So I can find solution for those. We talked about the path names, we talked about the relative path names and that kind of stuff. Let me talk a little bit about, because I'm going to talk about this linking and unlinking. Let me talk a little bit about how the directories are formed actually. And let's do this. Let's say we have this root directory. Inside this root directory, well, what did I say? Directories are actually special files, right? They are just files. That's it. So if it's a file, then it should have some content. Inside this file, I have this. For each directory entry, I have a record. Okay, this is directory bin, this is etc, this is lib, this is user, and temporary directory. Okay, and in each of them there are some attributes. I am not going to. Well, we know the file attributes like the last access time and etc. That kind of stuff. I am not going to talk about them, but there will be one pointer that points to some other file in my disk. So in this case, this bin entry will point to another directory, and it has its own fields too. And let's look at this user thing. User has this. Okay, it has AST, gym, lib, etc. Okay, and it looks like AST is pointing to another one, and it is a directory too. If it is not a directory, the pointer, it doesn't point to a directory, then it's a regular file. That's the structure. Okay, that's the structure. So these pointers are actually the block numbers. So that's the block number, or well, it changes. Maybe block number isn't a good term, but it changes from file system to file system. For the inode based file system, it is the inode number. For the FAT based system, it is the block number and etc. But it's a pointer. Okay, it's a pointer. So I am talking about this because because this is directly related to this procedure of directory linking or file linking and unlinking. We can say that, let's say I have a file in AST, it's just a file a.txt, and I like to share the same file from Jim. Okay, these are not copies of the same file. These are the same thing. Okay, these are the same thing. It is not the copy. It is the same thing. So when I modify that this a.txt, this is modified. When I read this one, I am actually reading this one, etc. You know what I mean. So how it is done? is going to be something like this. Remember this, inside the AST I have a.txt, okay, and this a.txt points to some memory location. Why don't I make this smaller, put it in here, and I can make it larger, right? Okay, so this a.txt points to a file in my memory. This is my a.txt. Inside this a.txt I have things. What was the other thing? The gem has a directory entry like this. Okay, from the gem again it has a.txt and it points to the same thing. Okay, so it means what? It means this. Whenever I modify the a.txt file under gem, I am modifying a.txt under AST. Okay, it is the same thing. I linked it. So the tree structure is not a tree structure anymore. It's like a graph structure, and I can change this through linking. But we say that there are two types of linking procedure. One is the hard link, the other one is the symbolic link. Hard link is the exact same thing. Hard link is the exact same thing that I have drawn here. Okay, remember these pointers are actually block numbers or the inode numbers. Gem has the block number of here under the gems directory. a.txt has the same block number as the a.txt of the other directory. So these are two different directories, but they contain the same inode number or the block number. Okay, this is called hard linking. Okay, this is called hard linking. Whatever the pointer type is, I am using exactly the same value for the hard linking. So it is very efficient. No problems. We can use this. The only problem that you may say it's a problem is that if this directory, okay, and the other directory this one, if they live on different file systems, let's say if this is a FAT based file system and if this is a inode based file system, their pointer types will be different, right? I mean, for the inode based file system, the pointers are inode numbers. For the FAT based file systems, pointers will be the block numbers. So how am I going to solve this problem? These are two different things. And you might say that how could this happen? I mean, how can you have two different users? How can you have two different users having two different file systems under the same drive? Well, in Unix it can happen. Remember, in Unix I have the root drive, root directory. Under the root directory I have many directories. One of them is the mount directory, right? Under the mount directory I can mount my C drive, E drive, etc. Right? I can mount many different directories under those, and so the files around here, they are inode based, but the file around here, they will be FAT based. Okay, so it looks like under this directory hierarchy, I may have files that belong to different file systems, and that's the nice thing about the Unix approach of the file system structure. So for that, they have developed this, they have invented this method of symbolic linking. Symbolic link basically is just a link. We are trying to share file, but since the files are on different file systems, I cannot just include their inode number or the block number. It doesn't make sense. So they say that let's create a very simple file, very small file, where I like to make the symbolic link. Okay, let's do it that way. And I am going to put the absolute address of the destination file in this small file, in this symbolic link. Instead of having two names point to the same internal data structure, because they can't. Okay, a file a name can be created that points to a tiny file naming another file. Okay, and their main advantage is this. Okay, and in Unix, it is easy to make symbolic files. I think yesterday I did it. Maybe I didn't do it. I don't remember. But I have some symbolic. Okay. When I say give me those, yeah. For example, this one is symbolically linked on this file. Okay. Mount C or C. So Mount C is my C drive. Obviously, since this is a Linux emulation, I am using, in this case, I am using a file system of Unix in this case, but I am linking to a place where the files are in NTFS, basically a Windows invention. It's a different file system, so I can do stuff like the same thing. I can do this. Okay, just give me the contents of that file or that directory. So the system thinks that it is my part. It is my entry in this directory, but it is part of some other directory. Actually, this is the function of the linking, right? So this is a the size of this file is very small, just 17 bytes. It just, I think it is this 1, 2, 3, 4, 5, 6, 7, 10, 11, 13, 14, 15. Yeah, it is 11 bytes, 17 bytes. Sorry, 17 bytes of data inside the simple file. And that simple file just it just gives the absolute address of the, in terms of path names, at the absolute path of the destination. And by the way, Linux knows this as a linked file. Okay, it's L. Okay, it doesn't say R. It doesn't say D. It says just L. Okay. So that's the story. That's the difference between the hard links and the symbolic links. Both of them are, again, ways of adding the same file to different directories. Okay, sharing the same file from two different directories, and it's a very nice way of sharing data, maybe, or not wasting this space by copying things all over. And sometimes we prefer hard links over the symbolic links because they are more efficient. Okay, but if you need to go over the border between the file systems, then you should prefer the symbolic link. Okay, what other operations do I have with the directories? Create, delete. Okay, opening it, closing it, reading it, renaming it. Well, other than this link and unlink, I have all of them with my files. And in fact, I can do linking and unlinking with the files too. Okay, I mean, you don't have to link only directories. You can link files too. But to link something, of course, you need a directory. Your destination is going to be a directory. Okay, any questions about these operations, about hard linking and symbolic linking? I think in Windows, only symbolic linking is available. That's what I think. How do you do the linking in Windows? You just go there and you say, for example, these are links. See, you see this small sign there? There is an arrow like a sign there, right? That's. Let me try to capture it and make it bigger. I don't know how to make it bigger other than that. So, what happened? Crop it. Oh yeah. Okay. So these are all actually, yeah, let me do this and make it bigger. Yeah, this is a directory, no linking. These are all linked, and these are all very small files. They are symbolic links. They are linked to, they are linking to some place on my desk, wherever they are. Okay, good. So, I mean, if there is a way of doing the hard link in Windows, I don't know. So how do you make a symbolic link in Windows? You just say You go there and you say create a shortcut. Yeah, kısa yol oluştur. When you do that, so now I have a symbolic link in here, right? So I can move this anywhere I like, and I can move this anywhere I like. It will be a link to this file. Okay, let me delete it. To understand something, if it's a symbolic link or not, okay, if I erase this one, this symbolic link doesn't make any sense anymore, okay, because it contains an absolute path. But if you have a hard link, you may delete one of the linked files. Okay? Say okay.
Okay.
Okay, thank you. Good. Any questions? Those who are doing their homework, please stop. Don't do your homeworks in this lecture, okay? Everybody is writing something. Don't do that. Especially that corner. You're too busy. Okay, thank you. Good. So let's go to file system implementation. Let's talk about how we implement all this kind of stuff. As ordinary users, we are interested in how the files are named, what kind of operations am I allowed to do them on them, and what the directory tree looks like, and etc. These are the stuff as a user I am interested in. But as the designers of the operating systems, okay, implementers, designers, okay, how the files and directories are stored on my secondary storage on my disk, how this space is managed, okay, and how everything should work efficiently and reliably, and by respecting the privileges of each file. So I think we are going to start looking at this part. I mean, up to now we looked at this part. Well, most of the things that I talked about you already knew one way or the other way. Okay. Now let's look at how the things are done in the operating system world. Okay. So file system implementation. Let's look at this file systems. What is a file system? File system is part of the operating system that makes decisions of how the things are done on our desk. Okay. So to do this, let's start from the beginning, and let's say, again, assume that I am using a desk. So this is my physical desk. On my physical desk, I write my data on tracks like this, concentric rings. Okay. One of these tracks are special. The outer one is the special one, and usually I divide my track into sectors. Okay, so each part is a sector. Now this is one sector, another sector, and another sector. Okay, so we say that there is a master boot record. It is the sector 0 of the desk. So this one here, this one is the sector 0. This one is the sector 0. Okay. This one is the sector 0. And the sector 0 is a special one because it contains this master boot record. When you boot your computer, okay, your BIOS reads this master boot record, and whatever it reads becomes your operating system, temporary operating system or permanent operating system. Okay, so your operating system is in here. Your homework, that guy who tells you how to do things on YouTube, you know that your real operating system that you did for homework number 1, actually the operating system that you have prepared, you have written it on the sector 0. Well, not exactly sector 0, but you had to modify the sector 0 to write your operating system. I'm going to tell you where you are writing your operating system in a few minutes. Okay, so sector 0 is something special. Okay, master boot record, and it is used to boot the computer. The end of the master boot record contains the partition table. So maybe I should show you this structure. Let's say this is my sector 0. The whole thing is my sector 0 in a linear way. At the beginning, I have my master boot record. After that, I have the partition table. Partition table will tell you how the rest of the disk, the whole disk, okay, this whole disk is organized. Because the whole disk is a very large place, sector 0 is only a very small part of it, how the rest of them is organized. Okay, it says that partition table is something like this. It's like a table, really. It has a name, for example, part 1 or part 1 system partition, partition for Linux, for example. These are partitions. Part 1 has to have a file system. Let's say this is NTFS. System is, let's say it is FAT32, and for the Linux it is EX3. Every partition can have a different file system. File systems are ways of storing your data on the disk, and the way of storing data on the disk changes. For example, this EX3, okay, Linux file system, it is inode based. It is indexing based. FAT32 or 16, it is based on file access tables, and we will see them in a few minutes. NTFS is kind of a continuation of this FAT32. Okay, so these file systems are different, and we say that this is the first partition, this is the second partition, fourth partition, etc. And I have all that information. We say that NTFS will start at this point, FAT32 will start at this point, EXE3 will start at this point, and I have the beginnings and the endings of the partitions. This is the partition table. Okay, and this table gives the starting and ending addresses of each partition. We said that, and one of these partitions in the table is marked as active. One of them is an active partition. For example, this one is my active partition. Active partition means that my operating system is contained in that partition. When you boot up your computer, okay, master boot record will give you these procedures, and go to the partition table, find the active partition. In the active partition, its structure is like, for example, in this case, let's say maybe I should change my partition, active partition, to this one. This one happens to be a Linux partition, EX3 partition. And the structure of EX3 partitions are like this, because it is inode based. It has this boot block at the beginning, then my super block, then my free space management stuff, inodes, the root directories, and etc. Okay, so this boot block actually contains this boot block. Okay, this boot block contains the real operating system. When the computer is booted, the BIOS reads and executes the MBR first. And the MBR inspects the partition table. From the partition table, it locates the active partition, and from the active partition, it gets the boot block, okay, and executes. And this is your real operating system. Okay, this is your operating system. So you put your real operating system in homework number 1 at this position in your active or chosen block. Okay, so this is what's happening. So we will be looking at these file systems one by one, different solutions to the same problem. How we solve this, for example, free space management. How we solve how we design our directory representation, how we address this linking problem. So we are going to look at these problems one by one, one by one, by seeing different approaches solving the same problem. Okay? Any questions? Let me move on then. This super block here, again, this is specific to Linux types or Unix type file systems. For the NTFS, the structure is different. So each file partition might have a different structure, but if you are looking at this one, the super block contains all the key parameters about the file system, and it is read into the memory. Okay? So this super block is usually kept in the memory, and it is very important. It keeps very crucial file system parameters and the variables. If you lose your super block, then you are doomed. That's not a good thing. Since I am keeping my super block in the memory, if my operating system crashes, I lost my memory, right? If I modify something on the super block, and if I didn't write it back to the disk, then I may leave, unfortunately, I may leave my partition in an unstable position, and that will be a big problem. Nobody will like it. Okay, so for example, NTFS or most Windows machines, they always write whenever you modify your super block or inodes, they always write it back to the disk. Whenever you modify this stuff, okay, Windows-based file systems, they write the data immediately back to the disk. So whenever there is a crash, I am safe. So it is safe, but it is kind of inefficient. Why? Because after each modification, writing it to the disk is slow, right? Linux doesn't do it that way. Linux keeps this kind of data in memory all the time. So all the modifications are done in the memory. So when do you write it back to the disk? From time to time, it writes it back to the disk, or when you shut down your computer, you say that I am turning off this computer, and Linux says that, okay, I'm going to write all the data back to the disk. Or if I am unmounting my disk, then I am going to write it to the disk. That's why I'm sure you experience this problem. You are using a Linux system, you write a file to your USB drive, you immediately take your USB drive out of your system, and you realize that there is nothing written to your USB drive, right? Did you experience this problem? Yes, you did. You didn't? Try it then, okay? Write something to your USB drive in Linux, okay? And after writing it, just take the USB drive out and try to see if that file is written. Try to see if that file is written. Where is that guy going? Okay, where is my attendance? When you take the USB stick out and test it in another drive, you will see that that file is not written because you did not update your super block and inodes on that thing. Okay, so that's going to be a problem. For Windows, this is not a problem because I always write it back to the disk. Okay, so super block and inodes we talk about it. So implementing the files. One of the important things, one of the crucial things to make a decision on implementing files is it is a contiguous layout. Okay, I am storing my files in a block by block fashion in a contiguous way, something like this. If this is my disk linearized, of course the disk is not linear. The disk is concentric rings, right? But if you linearize them, okay, if you think them as like a very long chain of blocks, I put my file A in the first four blocks, then file B 3 blocks. Let's say each block is 4 kilobytes. So this has 16 kilobytes of data, 12 kilobytes of data, and do it this way. It looks like very simple. So my directories, remember my directories? My directory structure in this case. So file A, okay, it points to this place, and file D, it points to this place. That's very simple, right? That's good. Very simple approach. Directory structure just points to these blocks, and linking is nice, and everything is good. So what is the problem with this approach? What kind of problem do you see it with it?
Disk fragmentation maybe? Disk fragmentation maybe?
Exactly. What do you mean with disk fragmentation?
Well, so the blocks in the disk, it's contiguous. So
Yeah.
if we have a very big file, we can't use small piece of memory
Yeah.
to.
If I delete this file B, if I delete this file D, I have a total of 8 blocks available, but I can't use them as a contiguous space, right? So then this is 5 blocks free, I deleted D, 6 blocks free, I deleted F, but I can't, I know that 11 blocks are available, but I can't put a single 11 block file on this disk, and that's called fragmentation. So how do you prevent the fragmentation? I compact my disk from time to time, okay? So move this file E and G front from time to time. This is not your memory. The things, moving things are very, very slow on this compared to your memory. So nobody prefers this kind of a thing. And you might say that, well, this is not going to work, maybe this contiguous layout. But some people say that, no, wait, don't hurry yet. Because for CD-ROMs, it is perfect, right? CD-ROM means that I am going to write it to the disk once, and I'm not going to modify it. I am not going to delete any files, okay? I am not going to delete any files. I am not going to modify anything. So why don't I use this contiguous layout for CD-ROMs, okay? So that's why the CD-ROMs has this kind of a file system. Contiguous layout, the files are written one after the other, and there is no way to modify them, or there is no way to delete them, right? And I can and the nice thing is that very simple. Once you know the starting block, reading is very fast. You start from a block and you read the next one, and next one. Fast sequential, also fast random access. I get all of them. These advantages, I cannot have external fragmentation for the CD-ROM. I am not deleting anything. I don't have any inflexibility about appending a file. I don't modify any files. I can't modify. So this is perfect. That's why CD-ROMs, they use this file system, okay? And for this file system, there is an ISO 9660, something like that. There is a standard for this kind of a file system. And if you follow this standard, any device that can read CD-ROMs will read your file system, okay? Good. So looks simple. It has disadvantages, but for CD-ROM world, these disadvantages are gone. Of course, for thank you. For the read-write CDs, I can't do that anymore. Because when you do the read-write stuff, you are modifying stuff, you are deleting stuff, you are moving them around. That's not going to be good. Okay. Is Yunus Emre here? Yunus Emre Yumşak. Yeşim Yalçın. Yeşim Yalçın. Okay, it looks like What are the possibilities that I catch the only person who didn't, okay? Tel Yeşim, Yeşim'e söyleyen arkadaşlar kaldı. Dersten gelmesin bir daha derse. Baştan başlayalım. Abdullah, burada mı Abdullah Çelik? Abdullah Çelik. Abdullah söyleyen kaldı. Ahmet Furkan Kurban. Ahmet Okur. Ahmet Tuğkan Aykan. Ahmet Tuğkan. Ona da söyleyin kaldı. Ahmet Yazıcı. Alp Emir Bilek. Berk Yiğit Dursun. Berkcan Ekici. Bilal Yalçınkaya. Buket Gençaydın. Burak Ceylan. Sen nereye gittin geldin? Gidin mi geldin? Sen buradaydın. Burcu Şuvak. Burcu, daha böyle kendine ait bir imza seçer misin ya? Bu güvenlik problemi. Sen paraf mı atıyorsun? İmza bu değil mi? İmza bu mu? Tehlikeli bir imza bu ya. Yani sadece initial bu şey yani. Caner Akın. Cihan Can. Çağla Şahin. Dücro, sen buradasın. Doğu Cem. Elif Koral. Emine Sultan. Emine Sultan. Var mı el? Göremiyorum ben. Emine'ye de söyleyin kaldı. Emre Sezer. Emre'ye de söyleyin. Emrullah Sağlık. Salik. Biraz önce çıkan arkadaş mı? Çıktı. Ona söyleyin kalmadı ama küstüm ben ona. Enis Yalçın. Enis'e söyleyebilirsiniz kaldı. Esra Er Yılmaz. Esra Sert. Faruk Ceylan. Fatih Doğaç. Fatih Sönmez. Feyza Nur. Ya yaptığıma bakın ya. Ne yaptırıyorsunuz bana? Feyza Nur. Diğer Feyza Nur. 2 tane Feyza Nur olduğu sürece hangisin? Efendim? İkiniz de buradasınız. Problem yok yani. Furkan Aydan. Furkan Çelen. Giray Yağmur. Gökbey Gazi. Hacı Hasan. Haktan Bilgehan. Harun Albayrak. Hasan Mutlu. Hatice Sevra Genç. Kaldı. Hüseyin Ömer Güray. Hüseyin Sarsılmaz. Hüsnü Akçak.
Burada hocam.
Gördüm. İbrahim Hilmi. İrfan Karatekin. İrfan, ismini sildim ya. Hocam ben buradayım de ben kalmadım. Ne kaldım? Tamam, geldi, şuraya geldi yazıyor. Böyle alt alta olunca seni de çizdik. Yaşın yanında yandın. Kurunun yanında. Yandın işte, her neyse. Kaan Can. Kevser Yolcu. Kıvanç Türker. Mehdi Kurt Cebe. Melih Yabaş. Melihcan Çilek. Mertcan Elçi. Muhammed Aşraf. Muhammed Bedir. Muhammed Oğuz. Muhammed Oğuz'a da söyleyin. Mustafa, ya söylememize gerek yok, burada kaydoluyor zaten, tamam. Mustafa Karakaş. Gördüm. Nevruz Yusuf. Necdet Dalaslan. Necdet. Nevzat Serferoğlu. Oğuz Mutlu. Ömer Faruk Bitikçioğlu. Burada mısın Ömer Faruk? Tamam. Öner Ercan. Öner de burada. Özlem Sevri. Refik Orkun. Salih Tangel. Salih. Sedef Erdoğdu. Sefa Çiçek. Selimhan Meral. Sena Erdoğan. Sena Nurul Kaya. Sena Nur. Serdil Anıl ünlü. Tamam Serdil. Sinan Sarı. Gördüm Sinan. Şeyda. Şeyma Nur. Tuğba Toprak. Ufukcan Erdem. Uğur Er. Yakup Talha. Yasin Akar. Yunus Emre Geyik. Yunus Emre Geyik, Yunus Emre Öztürk. Yunus Emre Yumuşak. 3 tane Yunus Emre, 3'ü de burada. Tamam, bu kadar. 1 2 3 4 5 6 yok 6 7 8 Enis Yalçın burada mıydı arkadaşlar? Enis Yalçın yok değil mi? Enis Yalçın. Tamam. Şunu şöyle yapalım. 7 8 9 10. Adım yok. Okumadın mı?
Yok, benim üstüm çizmişti hocam. Yani imza falan bundan sonra altı falan mı?
Ya yok, sen kaldın artık, çizdin bir defa. Emrullah'tın değil mi sen? Yok, Emrullah değilsin sen, yok. Geldi. Tamam. İrfan Karatekin değil mi?
Evet.
Tamam, geldi yazdım ben oraya. Tamam. Ya bunu niye yapıyorsunuz anlamıyorum ki ya. Dersin başında da söyledim yani ya. Tamam, benim için okuyacak daha az kağıt var. Okay, let's take 15 minutes of break. After the break we will continue.
Arkadaşına imza sınavları direkt kaldırmıştı.
Ne oldu?
Kaçırdım.
Kaçmadım ne oldu? Sana küstüm hoca. Yani rahatsızlandım mı sen? Kanka ben
Ama istiyorsan bir söyle.
ne söyleyeceğim ya? Şey mi oldu?
Yok, senin yüzünden.
Evet,
Senin yüzünden aslında
Sen
düşündüm
çıktığın için yaptım.
Ama yani cidden çıkasın, yani çıkmam lazım.
Sana küsmüş işte. Geri kalanları bıraktım.
Bıraktı mı gerçekten? Ben çıkarken hoca bir şey dedi. Ben duymadım mı?
Şimdi açıkçası.
Nereye gidiyor bu arkadaşımız dedi. Hiç fark etmedim yani. Sen geri döner misin?
Onlar gitmeden.
Mecbur başladım. Açıklayacağım ya. Yapacak bir şey yok. Neyse bizim aplikasını da gördüm. İmza atanları bıraktın mı? Ya bıraktım. Bakalım. Hoca çünkü
Kanka
derslerine
öğrendim
bakıyordu.
değil de gel beraber çözelim. Ben bir şeylere baktım.
Yapacak bir şey yok.
Finali var yani. Ben artık hiçbir şeyden. Final olur. Belki bir ödül yaparlar. Bilmiyorum. Valla bak şimdi bir tane soru buldum, tamam mı? Sınav sorusu. Ya bütün konuları kapsamış zaten. Bütün konuları birer bir insan herkes yapamaz. Diyor ki onu gösterin. O kadar çok patlatıyor. 2016. Sen laptop getirdin mi yanına? Bak beraber. Gel gel gel. dakika ama. Gözleri kamaştı. Öyleydi. Ben de niye maske yapmışım? Ne yapıyorsun? Sürekli maske yapıyorum.
Ya ben alamıyorum altı nefes ya.
Evet.
Yok.
Açıyorum yani. Öyle bir şey de var. O network'te çok büyük. Yumurtaları indirim yapmışlar. Niye ki? Fiyatını düşürmüş.
Yumurta mı?
Neden?
Yani bir şey vardır.
Bu hiç hayır alamet değil.
Evet doğru.
Genelde çıkması lazım.
Bana ne diyor?
Yumurtanın kurusu 50 lira olmuş.
Artık şey yapmıyorum. Çektim elimi ayağımı.
Ha, ekmeklerini
Evin çocuğu oldu. Uğraşmıyorum.
Öyle bir zor oluyor. Hemen anlatıyorum. Bana bir şey demesinler diye temizlik yapıyorum diyor, yemek yapıyorum.
Kız hiçbir şey yapmıyorum.
Sana bir şey demesinler.
Yok ya, şey yapmıyorum.
Şey,
Bir tek güzel patlıcan yemeğinde iyi olduğu için ben yapıyorum.
Ablamlar ne yaptı?
Hangisi?
İkisi de
Kübra da orada, o kardeşi.
bilmiyorum.
Bebeği göstereyim mi?
Bilmiyorum ne aldı?
Çok küçük. Çok çirkin.
Çok oldu mu?
2 hafta falan mı? Ya 2 ya 3
Yine
olacak.
normal değil mi?
Normal. Şey ama ya. Elinden ikisi zaryan oldu. Kız tam bir Urfalı geldi ya. Hiç alakası yok. Çok kolay oldu. Yine sancısı olmadı. Sonra sancısı olmuyor. Bizimkilerin sancısı olmuyor. Şeyin de olmuyor.
Annem de öyle dedi. Nesi küçük?
Kız yeni doğduğunu
Bu da bu kadar dudaklı.
Ay geçen de Ali'nin hasta oldu. Tam bir erkek çocuğu oldu Ali'nin ya.
Evet ya.
Sevmezsin kız çocuğu. Bu da tam tersi böyle şey böyle sıcak kitapları küçücük çocuğu. Ama biz kız çocuğuna benziyoruz. Alakası önemli.
So the contiguous layout is this. It is still useful. It is simple, but it is useful. So what is our solution for this contiguous layout? We say that we cannot put the five blocks one after each other. This is too simplistic. Maybe we can do this linked file allocation. Okay. So this is what we are going to do. Our directory, remember our directory structure. This is our directory, and these are our files. Let's say my file is file A. File A, and file A starts at block number 4. Here's the block number 4. Okay. I get to block number 4. I read it, and there is a pointer to the next block, which is block number 7. And the next block is block number 2 on the physical disk. So I distribute my blocks all over the disk, and I use this linked list structure. Okay. So this solves this problem of contiguous allocation. Now I can append any blocks as I like, because this is simply a linked list. I can append any number of blocks to my file A or file B. By the way, file A is 4 and file B is what? File B is 6. So this is pointing to here, and this is pointing to there. So this is the general structure, and very, again, simple. A little bit more complicated than the contiguous one. I can modify any file I like, and there is no external fragmentation, right? Because my blocks can be anywhere on the desk. I don't have to do any compaction. I don't have to move blocks around. That's very simple. That's good. But the problem is this. What was the advantage of contiguous allocation? The advantage, okay, fast sequential, also fast random access, right? Very fast sequential access. Why? Because I get to the, for example, if this is my desk, okay, if these are the blocks that I have allocated for file A, once I get to this position, I keep reading these one by one, okay? I keep reading these one by one after the other one. Since my disk is spinning that way, I am okay. So reading them sequentially is very fast. Reading randomly is fast too, because all I need to do is get the address of the beginning of the file, calculate the block that you are going to read. Let's say it is this one. Okay, immediately go there, because it is like array accessing. So sequentially and random accessly, sequential and in random access ways, it is very, very fast. But for this case, you are going to see, to access this last block of the file, to append something to this file, I need always start from the beginning, right? To insert something to this block, okay, to this file, I need to start from the beginning and follow, okay? Maybe you can say that sequentially it is okay, because sequential reading starts from the beginning and it ends at the end. That's fine. For random access, it is definitely bad, because to access the block number 3, you need to start from the beginning, and each time you are accessing a different place on your desk, you need to move your read-write head from one position to another position. That's a physical movement. You need your spin disk and etc. So random access is definitely a problem. Also, sequential access is a problem too. Can anybody tell me what the problem is with the sequential access? Sequential access is slow. It's not as fast as the contiguous allocation. Sequential access is slow too. Why the sequential access is slow? It looks like read this and this and this and that. Well, I can do it better than that, right? But no, it is slow. It is not as fast as the contiguous access, contiguous sequential access. Yes?
Because you need to jump.
Exactly. To read each block, you read the block number 0, right? After that, you need to get the second block's address. Then you need to rotate your desk, and you need to move your read-write head to some other position. I mean, these seek times and the disk spin, they will take time. It will take time. So it is slow both in terms of sequential access and random access. So all of our positives become negative. All of our negatives become positive compared to contiguous access. Okay. Advantages: space efficient, flexible in appending, and modification, no compaction, everything. But the disadvantage is sequential and random access is slow. So give me a solution for this. How do I make this faster? Linked list, I mean, I like to keep these advantages, space efficiency and flexibility in modification appending, making it large and make it shrink. But I don't want to be this slow. How would you do that? Yes?
Make them contiguous as far as we can.
Well, the problem is, well, I mean, yeah, that can make them contiguous as far as we can. Your suggestion is this.
Yeah.
Okay, if this is my file A, A0, A1, A2, then maybe A3, A4, and A6, right?
Yeah.
Maybe, well, this kind of solves the problem of the sequential access being slow, but it doesn't solve the problem of random access being slow, right? To access the 6th one, you need to go to this one, this one, this one, and this one, this one, this one, right? Again, and the other thing is this. Without reading A0, you would not know that A1 is coming next, right? You need to read A0 and read it and interpret it. Reading it while you are reading it, while you are seeing that, processing that the data, the next one is A1. It will take time, okay? By that time you realize that A1 is next, your disk has spun and it is not your underhead now. So that might be another problem. Your solution is kind of partially solves one problem, but at the end I will run into this fragmentation problem, not the external fragmentation, but fragmentation of my data distributed all over the disk, and it won't be much different than linked file allocation. Yeah. Well, I mean, we can do that, but not exactly the solution that I'm looking at. Yeah. Yes. Mm-hmm.
Can we use double connections?
Yeah. Double linked list. Yeah. Well, double linked list kind of solves this problem, but again, maybe appending to the end is going to become faster, but again, sequential access and random access is going to be slow.
Cache maps maybe?
What's that?
Cache maps maybe.
Cache maps, what do you mean?
Using cache maps instead of linked list.
Just explain what you mean.
So we can randomly access each element in the
Where do you keep your hash map?
side memory.
Inside memory. Well, okay. Why do you have the hash map then? I mean, you don't have to use a hash map. Just the suggestion is this: why don't we keep this linked list structure, only the linked list, not the data, in memory, right? That's what we say. In memory, I have a table. Table says that. Maybe. I think I have it. Yeah, here it is. Table says that. Okay. File. This is my directory again. File A, it starts at 4, and file B starts at 6. Okay. This is in memory. I go to memory. I go to my memory. I say that the file A starts at 4, and then the next one is 7, next one is 2, next one is 10, and next one is 11, and next one is 14, and 14 says that I am done. Okay? So these are all in memory. Since these are all in memory, okay, sequential access is random access. Let's look at random access. By following this link in my memory without going to the disk at all, okay, I can be very efficiently find the block that I am looking for. Okay, so random access is fast. For the sequential access, well, it looks like it is not as fast as the contiguous one, right? Is that true? It is not as fast as the contiguous, because contiguous one, I can read the whole track at once, and I have all the data in my hand. So this is not as fast as that way, but there is one big advantage of this architecture in terms of sequential access. What is it? It is better than the purely linked list approach of file organization. It is well, what is it? It is better than this one. Is better than this one in terms of sequential access. It is more efficient. It can be made more efficient. That's what I'm saying. Well, it looks like you read 7, you go to 7, you read 7, then 2, you go to 2, and well, you might say this is the same thing. You are reading blocks one by one. Hocam desteğim acil mi?
Yok hocam ben soradım hocam.
Tamam, çıkınca ararım. So I can take advantage of this structure in terms of sequential access. Very important advantage here. By looking at this table, I know that by looking at this table, file A contains blocks 4, 7, 2, 10, 12, and that's it, I guess. So without reading anything from the file, I know my block numbers, right? If I order them 2, 4, 7, 10, and 12, start from the beginning of the track, okay? Read them 2, 4, 7, 10, and 12, and optimize your disk access that way. So you know which blocks you are going to read at the beginning, right? Before you start doing your sequential access, okay? And as an operating system, if I am accessing my files all the way like that, and this is for file A, for file B I am going to do the same thing. if many people are trying to do the same thing, so I can optimize these kind of accesses. Say that, okay, while I am on this track, I am going to read this and this and this and this. So I can make it a little bit more efficient. Well, of course, it's not going to be as efficient as the contiguous access, but it will be more efficient than keeping everything on the desk. Okay. So this is called linked list table in memory, or sometimes we call this file access tables, FAT. This is file access tables, FAT, right? FAT 16, FAT 32. These are, for example, this FAT 16. 16 means 2 to the power 16, 16 bit. So this number here is just 16 bits. I don't know if I made it 16, but I think it is 16 now. Okay, so when you say 0, that you find a 16-bit number here, and that you go to that 16-bit number, you find another 16-bit number in there. So basically, it is you can have 2 to the 16 entries in your FAT table. Okay, file access table, 2 to the 16 numbers. So if each block is 4 kilobytes long, that means 2 to the 16 times 2 to the 4 kilobytes is 12, is it? So there will be total of 2 to the 28. So this is the maximum. This is the maximum addressable this size for a FAT 16 system, right? 2 to the 28 is 256 megabytes. No, kilobytes. What? Yeah, 256 kilobytes, right? Very, very, very small number. No, not but megabytes, right? It is kilobytes, megabytes, gigabytes. Yeah, 256 megabytes. It's not a very big thing, but FAT 16 is a very old file system. Now later they came up with FAT 32. Okay, with FAT 32, this number goes to 2 to the 46. Now we are talking about terms of terabytes. Okay. So that's how the FAT works. What is the disadvantage of this method then? It's nice. Random access is good. Random access is as fast as contiguous allocation. We can optimize the sequential access. These are all nice. These are the advantages. So, but what is the problem? There is always a problem, right?
So may I ask a question?
Sure.
But this system cannot solve the jumping actions.
No, it cannot. I can just optimize it. I can say that instead of accessing these blocks this way, I can access them this way. Later sort them in my memory. Okay, so I am kind of helping it, but I am not 100% solving it. I solved the random access problem 100%, no problems. Sequential access, no. Like you said, maybe try to keep your blocks contiguously as far as possible, as much as possible. That's one thing. If you can't, I will organize your access block access orders in memory, and I will ask the operating system or the driver to access those blocks. So I answered your question. Now you answer my question. What is the problem with this? Yeah, the primary disadvantage of this method is. Did you suggest this solution? You said that let's keep a hash. This is not a hash. This is just a regular table. So, what was the problem with your solution?
Collision?
But we don't have no collision. We don't have a collision here. It's not a hash table. It's just a regular lookup table. We are not talking about hash. We are talking about this table, lookup table, right? We keep the linked list in memory. Okay, we keep the linked list in memory, but the data stays on the desk. So this linked list part is in memory only, right? The data, those 4 kilobytes of data, stays on the disk. So what is the problem? What is the size of this table? 2 to the 16, right? 2 to the 16 entries, 2 to the 16 entries for this table, and each entry is 2 bytes, right? So it is 2 to the 16 times 2 to the 9, right? Is that correct? What? No. Byte is 3 for 2 to the 4. Okay, so this is 2 to the 20. 1 megabyte of memory required, right? 1 megabyte of memory. Well, I mean, when you had this FAT16 systems, your maximum memory for a PC used to be like maybe 256 kilobytes, maybe, well, at most 1 megabyte. I can't use my whole 1 megabyte of memory to keep this thing in my memory. Okay, that's the disadvantage. The primary disadvantage of this method is this FAT table becomes large. Okay, it becomes large. So that's why they invented this FAT16 and later FAT32. If you have memory, well, nowadays 1 megabyte is not much, but nobody uses FAT16 anymore. We kind of use FAT32. And for FAT32, you know, we are talking about 1 gigabyte of memory to keep this data. So we have to either page it in and page it out. Use that kind of a solution. So the direct solution like this and keeping the whole FAT table in the memory is problematic. That's one thing. The second thing is what? What is the second thing? I make all of my modifications in the memory, right? I make all of my modifications in my memory. If I don't write this FAT structure, file access table, back to the disk, if my system crashes, I lost all of my modifications on the disk. So I will have inconsistency between the disk and the memory. Okay? So that's going to be a problem. That's why, again, the Windows does it that way. Windows says that whenever you modify this FAT structure, file access table, okay, it immediately writes the modification to the disk. That means that every modification here will be a disk access. That will make things slower. For reading, there is no problem. If you are reading only, then there is no modification and no problem. But if you are writing it, there will be lots of disk accesses. So that will kind of cancel away the advantage of having this table in memory. But it is still better than pure linked list allocation. Okay. Good. So this is the linked list table in memory. Okay. So advantage of linked list, no disk access. Disadvantage, still need to traverse and lots of memory required. So 200 gigabytes of disk, 1 kilobyte blocks. So if I have 200 2 to the power 30, I have 1 kilobyte blocks, 2 to the 10. That means what? I have 200 times 2 to the 20 entries. Okay? We are talking about 200 megabyte of FAT, 200 megabytes of FAT size, and that's going to be big. 200 megabytes for a single disk. Okay, so the solution is you are paging it. Okay, you are going to divide your FAT structure, file access table, into pages, and you load only the pages that you are using. Okay, so people thought about this. Maybe this is usable for small disks and primitive operating system like the Microsoft MS-DOS, etc. So let's come up with something. As always, it will come from the Unix side, it will come from the multi-site, they have invented this index allocation, inode structure. Inode. Okay? So it brings all pointers together into an index block. So these pointers will be collected in a special block and they will stay on the desk. Okay? For each file, I will have index blocks. For each file, I will have index blocks. And inside those index blocks, okay, I keep that fat structure. Okay? Brings all pointers together into the index block. Just keep all attributes and addresses of each block belong to the file in the structure. And keep this block only in memory when the file is open. So this one keeps everything in the memory all the time for the whole disk. Index structure says that when the file is loaded, loads its inode, index node, index block. Okay. When you're traversing memory, traverse your memory using those blocks. Okay. So keep them in memory when the file is open. That means what? You don't have to keep all the maps of the disk in your memory all the time. Only the files that are opened. So the advantage is space efficiency in terms of course, memory space efficiency. No external fragmentation, no overhead of index blocks. Okay, no overhead of index. No overhead of keeping indexes in your memory, but this time now I have to have this index blocks. To keep this data for each file, you need to store them on your disk. That's why you need to have inodes. Remember this structure? There is a special place on your file system. If you are an inode type operating system, file system, okay, there are many inodes available, and each file, okay, say that, okay, my inode is this inode, my inode is this inode. So you kind of allocate inodes from this inode resource, and inside these inodes we have these small file allocation tables. Okay. Inside these inodes, we have these small file allocation tables. So whenever that file is opened, I open these and I keep them in my memory. I never write them back unless the file is closed and system is dismounted. So Unix does it that way. It never writes it back. It always keeps it in memory. So when you crash, if you crash a system, Linux system, there is a very serious problem of losing this data, because you don't write these inodes back to the disk immediately after modification. Okay, that's the inode approach, and let me show you. Okay, random access is fast, sequential access is as fast as it can be, and this is a simple inode structure. This is just a block, 4 kilobytes of block, simple block. In this block, it's a special block, it's called inode block. Okay, in this block I have the file attributes, then I have the address of the block number 0, address of the block number 1 for the file, right? So all of them, or 7 of them. Okay, and then if 7 blocks are not sufficient, if 7 blocks is too little for me, then you will have a pointer to another inode. Okay, disk block containing additional disk addresses, and we do the same thing there too. Okay, if I have enough pointers in this block, then I am fine. Otherwise, the last one will be another inode block. Okay, so that way you are doing indexed accessing. Random accessing is okay. You load your data, you load your inode data to your memory when the file is opened, and I don't have to keep the indexing structure for the whole disk in my memory, only for the open files. If you have too many open files, then that's going to be a problem, right? But most of the time operating systems will restrict you. They will tell you that you have opened more than 200 files, I cannot keep doing this, okay? There is a maximum open file limit for the operating system, like the maximum memory, something like that, okay? So there is a limit to these inodes, so the number of inodes that you are keeping in your memory at the same time. So we kind of handle that problem. Other than that, no problems, okay? So this is how the indexing and the Unix file systems work using the inodes. Okay, good. Any questions?
So,
Yes.
so this table exists in disk or memory?
This table is specific for each file. Each file has this table, and they are contained on the disk. Okay? When the file is opened for reading or writing, this table is loaded to the memory. Yeah. So you keep them in a special location. You keep them in a special location, inode location, okay, on your file system. Usually you keep your inodes, let's say this is your disk. This is the center, okay? This is your, let's say, read-write head. It is like this. So I can put, I can push this in and pull it out like that in a very, very fast way, okay? Usually you keep your inodes around this track because on the average, this is the closest track that you can go to. On the average, it is the fastest track that you can reach, because doesn't matter if you are here, sorry, you just push your read-write head forward a little bit. If you are here, you just pull it a little bit back, so it is in the middle, right? So you keep them in a special place, and you carefully take backups of your inode partition of your file system. So you take special care of it. Nobody is allowed to access that part other than the operating system file system part. Yes?
Does all of this and before work similarly for the SSDs?
All of this and before works in where?
Does it work, all of this and what we mentioned in the last class, does it work similarly for the SSDs? I mean, I know they don't have the pins and needles. And this
NSFT, NTFS?
No, we are giving examples for the disk, and then you say there is a pin. So
Oh, you mean the SSD?
SSD, yes.
Yeah.
So
Well, sure, yeah. Well, for the SSDs, the file systems are a little bit different. I mean, that's a very good point. We are always talking about the disk accesses and the tracks and that kind of stuff. Yeah, the SSD file systems, they are very similar to this, because you need some indexing in the SSD files too. For the SSD, accessing SSD is slower than accessing your memory. So you need to load some indexing structure to your memory. That's true. But SSDs has some other problems, like you cannot keep writing to the same block on SSDs, because SSDs has limits on the number of accesses. If you access the same block more than 1,000 times on an SSD, okay, it will die. That's the technology. That's why they don't keep their inodes in the same place all the time, because you keep accessing your inodes, you are going to kill that part of the SSD. So they usually try to move things around, okay? So they have structure like those for the SSDs. Yeah, they are using the same indexing structure, but there are other things to consider when you come to the SSD file systems. But basically, you keep your data as in terms of blocks, okay? And you need one way of knowing which blocks should you access randomly. And sequential access is very fast for the SSD. It doesn't matter where you are accessing, right? I mean, you don't have the mechanical speed overheads for the SSD. So sequential access is fast, both for the linked structure and the contiguous access or the index access. Okay, good. So we talked about the inodes, and let's go back and let's talk about the directories. I kept talking about the directories like this. I said that this is my directory, and there is a file name and there is a pointer, right? That's what I said. And maybe at some point I said that there are attributes in here too. So the things are a little bit more complicated than that. Let's look at those details. Okay. Again, the structure of the directory depends on the system. Okay. First, the directory has to keep the files, and if I am using the inode structure, this pointer is a pointer to an inode. If I am using the fat structure, this pointer is the block number. If I am using something else, again, this is just a pointer. It changes from system to system. Okay. So in any ways, for all the cases, this main function of the directory system is to map the given not ASCII name, given the name, string name of the file onto the information needed to locate the data. So I am giving you inside this directory, I am giving you a name file b.txt, and this structure is responsible for taking this file b.txt and finding this pointer and giving it to me. After that, I am just opening that file. For the inodes, I load all the inodes. For the fat-based system, I maybe load the sequential blocks and etc. So this is one example of directories. I have 1, 2, 3, 4 files in my directory, and these are the attributes. And within the attributes, I have these pointers. Okay, I have these pointers. Some systems, they keep all their attributes in the directory structure. Some systems, they keep their attributes in a separate block, disk block. Okay, so the advantage of this one is obviously I can have very large amounts of attributes, for this approach. For here, the amount of attributes you can have is limited. Okay, maybe the read, write, execute privileges, the owner, last access time, and etc. Nothing more than that. For this one, you can have many attributes as you like, because this is a whole block, and if you like, you can have a linked list structure for this kind of an approach. Okay, for this kind of an approach. What kind of attributes you have for the large system? For example, I can keep versioning data. I can keep the previous versions of the file as my attributes, right? Very large amount of data as your attribute. You can talk about, for example, remember the picture that I showed you last time? Can I do this? Properties, and yeah, if I go to the details, well, this is not a good one. Maybe I should open if you open a picture that is taken by a digital camera puts lots of metadata as attributes to your image. Do I have any images? I don't, maybe this one, screenshot. Yeah, as you see, I have many things like the title and subject and my feedback about this image and etc. and the other stuff. Where did I take this picture? Who took this picture? What is the resolution? What is my bit depth, and etc. See, I can have this kind of information for my file. It is only specific for image files, okay, or digital image files. For the Word file, I don't have these kind of details. I have maybe other kind of details. For these kind of cases, this structure is more suitable. Okay, this can only keep a limited amount of data because my attributes are limited. Okay, so most systems, modern systems, implement a structure like that. One example for this kind of thing, I mean, remember the MS-DOS limitation of on the characters, the number of characters of a file. It says that you can have 8 character file names and 3 character extensions, right? So that's because I have only 11 bytes available for the name field. Okay, if I like to make this name of the file unlimited, you can have a name of length 1000 bytes, 1000 characters, then this will not work. You need to have something like this. Okay, so this will be pointer to file one's name, file one attribute. So there is a pointer to some place on the disk, and I can put my file name on that place, as many characters as I like. Again, for the second file's name is there. For the third file, it is there. Again, I can do the same thing for the attributes too. Okay, so each entry is like this. So this is one entry, this is another entry, and this is another entry. It goes that way. Or if I am going to use the fixed size for each entry, okay, this is the first entry, and this is the second entry, and this is the third entry. It's entry size is fixed. That's why you cannot have longer file names. Or if it is not fixed, if you can continue with your file names like that, then to access your third element in your directory structure, you need to do the sequential access. Read the first element, calculate its length, find its length, then read the second one, then read the third one, and etc. In this structure, you know where your 5th file is on my directory. Okay, 2 different approaches to implement long file names in a directory. Okay, good. So all the modern operating systems, they use they don't put any restriction on the number of characters in your file names, or they can have a very large amount of data for as your metadata or attributes, and this is what they use. Okay. Another problem that often comes up with the directories is this: if you have, let's say, 10,000 files in a directory, it might happen, right? Well, it's not a good idea to have 10,000 files in a directory, but sometimes you can have them. Finding a file, let's say I'm trying to say ls.abc.txt. Just give me the listing of that abc.txt in this directory, and there are 10,000 files in there, right? So what am I going to do? I will make a linear search, right? And making a linear search on this 10,000 elements in a single directory is going to take some time. So one approach is to use a hash table. Just hash this string, make a key, and make a key on this string, and look it up from the table and find if the listing is there or not. If it is there, then list this file along with its properties. Okay, or maybe I can load all that data to the memory and make the search in my memory, which will be much faster. Okay, so that's one optimization. Of course, we are talking about directories. These are files. They are on the disk. When I say search for something on the disk, it takes longer to make a search. If you bring all of them to the memory and make your search in there, that's going to be faster. Good? Any questions? Okay, let me move on then. Shared files we talked before. Okay. I like to share this file between these two directories, B and C. Okay, B and C. The problem is this. Most of the time the problem is this. If it's a symbolic link, well, I don't see much problem in this. Okay, if it's a symbolic link, because symbolic link means that somebody owns a file. That file belongs to this directory. I am only keeping a pointer to that one, an absolute path for that one. No problem. The problem comes with the hard links. Okay, the problem comes with the hard links. Okay, in that case, all you are doing is with the hard link is you are sharing your inode number or the block number, but the ownership of those kind of files become problem. If C is a different user than B and C are two different users. Okay, if I make a hard link for this file here, who owns this file? Sometimes it becomes important. Let's look at this problem. In C's directory, I have a file. Okay, for that file, I know that I own that file. The owner is C, and the number of directory entries pointing to that file is just 1. If somebody else is pointing to that file now, I incremented the count to 2, so I know that 2 different directories are pointing to the same file, so it is shared using a hard link. No problems. But if I delete this directory, C directory, now B points to a file that belongs to owner C. The worst thing is, maybe the system administrator removed the user C from the system. So I have a file owned by somebody who is not on my system anymore. Okay, and he or she has the modification privileges. So this looks very much like shared pointers of C++ or the references of Java, right? But in that case, of course, we don't have any owners of data, right? So we need to be careful about this kind of stuff. If you are the only pointer to that file, and maybe you should be the owner of that file, or maybe just a degenerate case, just ignore this one. Your file system has a problem like that. It happens. Yes?
If the file that is shared between B and C is deleted by the owner, is it deleted in B's directory also?
No. Well, I did that yesterday, remember? I made a hard link. Remember this one? Let's make this one. Let's try to Alan is a link one. Let's try to go to CPP test and a.out. CPP test a.out, and I linked it in here. Okay, where is my a.out? It's here, right? It is linked, and it is hard linked. Okay, and there is an a.out here. A.out in here, then there is an a.out in CPP test. Okay, both of them are exactly the same thing. If I remove the other one, this will not be there, but this will be here, right? Okay, so if you that's the meaning of the hard link. Let me move this a.out back to CPP test. Okay, let me make a symbolic link -s CPP test and a.out here. Okay, .s. Okay, so this is a symbolic link now. A dot out. Where is my A dot out? Yeah, it is symbolic link. Okay, let's remove the CPP test A dot out. Okay, now list it. It is still say that I am pointing to CPP test A dot out, but I removed it. If I try to, for example, what do I do? Let's say, yeah, cat. Do I have cat? Yeah, I have cat. I cat CPP A dot or no, cat A dot out. Okay. It says I can't find anything like that. I mean, even I have this file A dot out here. It is pointing to the CPP test A dot out in my directory, but that file doesn't exist anymore. That's the difference between hard linking and symbolic linking. Okay, but with the hard linking, you have this problem, these problems. With the soft linking, maybe using ownership problem can be addressed using the symbolic links, because once you remove it, it is gone. Everybody knows that. But we don't like the symbolic links because, I mean, for the symbolic links, you need to make a new small file, and opening that file, reading it, makes it a kind of slow, right? And it occupies some disk space. So hard links are more preferred way of sharing files. Good. Any questions so far? It looks like I'm out of time. Next week, I guess it is Bayram, right? Holidays for 2 days. We will not hold any lectures, but that means that during the makeup time at the end of the semester, I will hold 2 or 3 hours of extra lecture. I will not let this go, right? So, okay, happy holidays. Şimdiden herkesin bayramı kutlu olsun. Kalan arkadaşların da bayramı kutlu olsun bu arada. Ne yapayım bilmiyorum ki adamları ya.